Sure, whatever is the usual.
I guess we can get started. So very happy to have Leah Jenks visiting from KICP. So Leah did her PhD at Brown, and now a KICP fellow at Chicago. So she'll be telling us about gravitational production of dark photons.
Great. Thank you so much for the introduction, and thank you all so much for having me today. It's great to be at NYU. The last time I was here was kind of in the midst of the pandemic, so it's nice to be back when things are more open and lively. So yeah, I'm going to be talking today about runaway gravitational production of dark photons. And I should say that everything I'm going to talk about today is based on these three papers. I'll mostly be talking about these first two, but we'll mention this last one a bit at the end if there's time. And this is all in collaboration with my very wonderful collaborators, Rocky Cobb, Evan McDonough, and Christian Cafanelli. Okay, great. So just to give everybody an overview of what we're going to be discussing in this talk. As I said, I'm going to be discussing gravitational production of dark photons in the early universe during inflation. And I'll show that this procedure can produce the dark photon, dark matter in the correct relic abundance that we see today. However, if we add non-minimal couplings to gravity to this theory, this can induce instabilities, such as a ghost instability and what we call a runaway instability. But there is a region of the parameter space where we can avoid these instabilities to think about dark matter and phenomenology. And then lastly, at the end, I'll discuss how these same results for dark photons can be applied to the Kalb-Ramond field and Kalb-Ramond-like particles. Okay, so as I'm sure I don't need to tell anybody in this audience, but just to recap, dark matter makes up about 25% of the energy density of our universe, and we have very little idea what it is. We know it exists because of its gravitational interactions, but we are very unknown as to what its actual particle nature is. So there are a whole zoo of dark matter models, which I really like this graphic here from Tim Tate, that really span a wide variety of model space, masses, charges, production mechanisms, etc. And so the way that I really like to think about how little that we know about the dark matter problem is by thinking about the mass range. So on the very light end of proposed dark matter candidates, we have ultralight axions, which can be as low as 10 to the minus 22 electron volts. On the very high end, we can have black holes or primordial black holes making up some or all of the dark matter, which can be order solar masses. And then, of course, in the middle, we have kind of the canonical WIMP. And so this is 90 orders of magnitude in mass, where we could have a potential dark matter candidate. And this is a lot of parameter space to really understand and look through. And so I think it's important, given this scenario, that we are really able to kind of fully understand the phenomenology of all of these dark matter models to think about what is well motivated and where should we really be looking for these things. Okay, so there are many different ways that dark matter can be produced. The one that I'm going to be focused on today is cosmological gravitational particle production, or CGPP, or GPP, as I will call it. And so this is a very old idea going back to Schrödinger in the 1930s, which discusses how the expansion of the universe produces particles. And so this is particularly relevant during inflation when the universe is exponentially expanding very rapidly. And the basic idea is that we have particles which are pulled out of the vacuum by the expansion of the universe during inflation. And so to make this a little bit more mathematically precise, we can think about this in the context of kind of basic quantum mechanics and thinking about two sets of operators at early and late times. So here by early times, I mean kind of before at the beginning of inflation, and by late times, I mean after inflation, so not late times as in like today. So if I have two sets of operators, this AA dagger early and AA dagger late, These operators evolve throughout inflation, and they are not equal to each other. And so if I take, for example, the early annihilation operator acting on the early time vacuum, I get back 0, just as I would expect. However, if I have the late annihilation operator acting on the vacuum, I don't get back 0. And so this is just basic quantum mechanics, and this is the basic idea of how gravitational production works. And so this here corresponds to particle creation. And you can characterize the number density of particles produced during this procedure with the following expression in terms of A and A dagger. So these two sets of operators, these early and late time operators, are related by these expressions here, where this alpha and beta are Bogoliubov coefficients. And so the coefficient that we're going to be really interested in is this beta here, which can be written in terms of mode functions of whatever particle it is that we're interested in. And so we can mathematically write down this beta squared in terms of the mode functions chi-k of whatever particle it is we're producing, and I'll explain a little bit more what these chi-k's are in detail in a few slides. And then this is also dependent on the frequency omega of this field. And so from this calculation of beta squared, we can go ahead and calculate the particle spectrum in terms of k, the co-moving wave number, and then integrate over all k's to get the co-moving number density of particles at the end of inflation. And so a couple things that I really want to emphasize here are that this is a very simple setup. So the only thing that this mechanism requires is that you have some inflating spacetime and some spectator field on top of it. You don't need any additional physics, and in fact, this mechanism happens whether you want it to or not. So if I have my inflationary universe and I have some additional field that's present, you will get gravitational particle production regardless of whatever else you're trying to do. So this is a very simple, kind of elegant setup to produce particles in the early universe, and this is going to be what we're going to focus on for the rest of the talk.
So what's chi?
Chi is the mode function for whatever your spectator field is. Yeah, any other questions on the setup? Okay, great. So I should say that there are many ways to calculate GPP. There's kind of a long history of study with this. There are many analytic methods that you can use to kind of characterize this process. For the rest of the talk, I'll be discussing specifically numerical methods, but there's other ways to do it as well. And then I should also say, as I mentioned, this is a very generic procedure that works for a wide range of particles with different masses and spins. So I'm going to be speaking about spin 1, but you can also do this for fermions, for scalars, for spin 2 particles, etc. So there's a really nice review by Rocky and Andrew Long if you're interested in some more of the details of GPP. Okay, so I'm going to be discussing gravitational production of dark photons specifically. So a dark photon is just a massive spin 1 field for these purposes, or a Proca field. I'll use these three terms interchangeably throughout the talk. They all mean the same thing. And this is characterized by some field A mu, which has a field strength F mu nu, which looks very much like the photon of electromagnetism, but of course it has a mass in this case. And so this is some dark sector, not the standard model. And so we can think about dark photons in the context of the dark sector in a few different ways. Often people think about dark photons as a portal to the dark sector. So for example, you can have some dark matter candidate that couples to this dark photon and can also couple to the standard model photon via some kinetic mixing that looks like this, where you have an F mu nu dark, F mu nu standard model. And there are a lot of observational consequences of this that have been discussed in various papers. None of these reference lists are exhaustive, so I apologize if I've left off your favorite paper. So we can think about dark photons as a portal. We can also think about them as the dark matter candidate themselves, which is mostly what I will be discussing. So in this case, the dark photon, A mu, is in fact the dark matter, not just some portal to the standard model to talk between the two. And so there has been quite a bit of work in the past few years showing that you can actually have dark photons produced via this particle production mechanism. And we can also produce these via processes like freeze-in and misalignment, et cetera, et cetera. So again, I apologize if I've left off your favorite production mechanism, but this is just an example. And so all of these works that have thought about particle production in this way have looked at this action, which is kind of the standard thing that one can write down. But we can also add non-minimal couplings to gravity. So the action that I wrote down before, we call the minimal theory. Minimally coupled to gravity. But we can also add these two additional couplings, which I will couple with these parameters C1 and C2. So the two dimension 4 operators that I can write down that obey the symmetries of this theory are a coupling between A mu and the Ricci scalar, and then a coupling between A mu, A nu, and the Ricci tensor. So if I set these couplings to 0, I just get back the minimal theory. But generically, again, I can write down these couplings. They're dimension 4 operators. They obey the symmetries of the theory. But also, we expect these couplings to generically be generated if you start to consider things like loop corrections or self-interactions. So it's very generic to consider these. Yeah.
Very naively, I would expect this production mechanism to sort of happen at a very high scale, or I might also worry about the UV completion, like the mechanism that gives me my mass from my dark photon, like an abelian-Higgs mechanism or something like that. Is that something you've thought about at all, or is it just like this Proca action?
Yeah, so for the context of this, we've just thought about this in the context of this kind of EFT. Sure. You could certainly do the same thing for like an abelian-Higgs model, and you would, I think, get similar results. But so we've thought about it a little bit, but this is mostly just based on this like Proca EFT. Yeah.
Just in terms of the field basis, you can do a field redefinition of the graviton. You can send G mu nu to G mu nu plus stuff that would transform these operators into F squared A squared and F mu nu squared A squared, respectively. So those no longer look dimension 4, but are really dimension 6 divided by M Planck squared, and the physics is completely equivalent. So I'm just wondering. Is there a reason to write it in the field basis where it looks like it's coupled to gravity and looks like it's dimension 4, but is actually dimension 6? And yeah.
Yeah, I think you could equivalently write it either way, and like you're saying, the physics I think would be the same. We just chose to write it this way, kind of for simplicity.
And matter couples to G mu nu, I suppose, in this framework, right? So your ordinary standard model couples to this G mu nu,
Right?
correct? So unless you wanna screw up that coupling, you better work on this basis.
Well,
but you can also work in that basis.
The field redefinition here of G mu nu that I'm talking about is G mu nu plus something that's higher order in derivatives. So you wouldn't screw up the minimal coupling of the standard model to gravity at 2 derivative order.
I didn't mean screw up in that way. I meant that you would change it dramatically so that the standard model equations of motion will have those additional pieces in them.
Only modulo, only in the EFT.
Sure.
Yeah.
And the CFT as well. So.
Yeah, so we chose to work in this basis, but I think everything I'm saying will also apply if you choose a different basis as well. Okay, so proceeding, assuming this is kind of the generic setup that one should consider, we can ask 2 questions. So the first is how does the addition of these non-minimal couplings, C1 and C2, impact dark photon production via GPP? And then I should also say there were a few other papers that came out around the same time as ours that looked at some additional aspects of this as well, to think about the impact of these couplings. And then the second question is, having determined this, what are the allowable values of C1 and C2 that we can avoid potential instabilities in the theory and produce the correct relic abundance of dark matter? So this is what I'll be focused on for the rest of the talk. Okay, So the main effect of having these non-minimal couplings is that we now have time-dependent effective masses in the theory, which you can see from the form of the Lagrangian. And there are two effective masses that appear, which we'll call mt squared and mx squared. And so if you decompose this on an FRW background, which is what we're thinking about during inflation, these have the following form, where again, R is the Ricci scalar, and H is the Hubble parameter during inflation. And so what you'll notice here is not only are these masses evolving in time, they are also not necessarily positive definite, because these quantities oscillate. And so these are not necessarily positive. The effective mass can become negative, which is going to be the source of some of our instabilities.
Just a quick question. So,
Yeah.
so you would be mostly interested in production at the end of inflation? Because
Yes.
during, okay.
Yeah, so this is kind of end of inflation into reheating
I'm sorry, I missed a very important detail. Effective masses of what?
of the dark photon.
Thank you.
Yes, yeah, so this M here is just the dark photon mass.
What is MT and
So these are just combinations of these parameters that I have defined as like an effective mass term.
but like does T and X mean anything important here, or these are just two different
These
methods?
are just naming conventions.
But probably that's also coefficient of A0 square versus AX square in inflation.
Yeah, they're related.
And R is the 4D Ricci scalar, H is A dot over A, it's some FRW.
Yes.
Slicing.
Okay, and so we can now discuss getting back to this question about KICP and the mode functions. So this is a massive spin 1 particle. So there are 3 degrees of freedom. There are 2 transverse modes and a longitudinal mode. So the transverse mode equation looks like this when you decompose it, where AT is just the transverse mode of the field. And omega t in this case can be written as k squared plus a squared mx squared. So again, dependent on this effective mass. We're going to be less interested in the transverse modes throughout this. All of the interesting physics is in the longitudinal modes, but I just have this here for completeness. So the longitudinal modes are a little bit more complicated. So we can once again decompose this field into this AL, the longitudinal part. And you'll notice that there's now this coefficient in front of the derivative term, and then similarly this effective mass on the mass term. So in order to canonically normalize this field, we define the function chi and this kappa squared parameter, which is dependent on both k, which is the co-moving wave number, and mt squared, this effective mass. And so once we do this normalization, our mode function, our mode equation looks much nicer in terms of this function chi. And so you'll notice also that again, these masses can oscillate through 0. They're not necessarily positive definite. Therefore, kappa squared is also not necessarily positive definite.
And sorry, wait, the A in there is against the scale factor.
Yes, sorry.
So it's growing exponentially during inflation, this kappa squared? Or no, because you have exhibit denominator, but why does it depend on A, I guess is my question. I would expect it to depend on invariant quantities like H or R.
Yeah, so this is just if you decompose at the level of the Lagrangian on a generic FRW background, you get some factor of A in front. It also does depend on H and R through the effective mass term, through the mt squared.
But you're right, Matt. If you pull out A square, you see you're gonna get
Yeah, A over A,
you
I
got
guess,
physical
yeah.
momentum squared
Yeah,
and
yeah,
physical
yeah,
that convolution.
yeah,
So
Okay, so we get this nice looking expression for the longitudinal modes, but this is actually hiding a lot of complexity. So within this very nice looking equation, this omega squared has a bit of a nasty looking dispersion relation, where this is now a function of R, H, and its derivatives and their second derivatives. So these are then time derivatives here in conformal time of the effective masses. But in this whole expression, the real term that we're going to be mostly interested in, the one that you should pay attention to, is this first term here. And so you'll notice that in front of this k squared, we have this function mx squared over mt squared, which is effectively a modified sound speed for these modes. And so this will be where a lot of the interesting physics comes from.
Yeah, Matt already asked this, but I'm still confused. So the R is equal to Hubble squared times some numerical factor, right? But here you have Hubble squared and R remaining still. So what does the R mean? Do I plug in a dot over the a dot over a piece there again, or no? Or is this the R of like the perturbations?
Yeah, so this is just, again, R, like the normal background R. You could write this in terms of H squared. Just to keep everything explicit, we left it
Okay.
explicitly,
There's
but
H
you,
dot in
you
there.
could do this.
Yeah.
Yeah, because this is for general FRW.
Yes.
For inflationary one, R will be H squared times constant.
Sure.
For general one, it will have,
Okay.
derivatives.
Yeah,
in
so
it.
there's
That's-
some-
That's why there is a difference.
Okay,
Yeah,
got it,
the
got it.
difference.
Does it-
There's some evolution,
That's
right?
right.
Like
Sure.
it's not just de Sitter or something like that.
Yeah.
Was there another question? Okay, great. Okay, so. Okay, so now we can get into potential instabilities in this theory. So the first is that there's a ghost. So as I mentioned 2 slides ago, we defined this parameter kappa squared in order to canonically normalize the field. This kappa squared is not necessarily positive definite because we have these effective masses which can oscillate through 0.
Okay.
Yeah.
Sorry if this is too naive, but the ratio of the two masses, mass of chi and t, so they are constrained by some kind of causality, right? Because it's related to the speed of sound in the manifold. So you don't want this to be superluminal, no? So this ratio is give you some bond.
Yes, yeah, so we'll talk about that in a couple slides. But yes, a good point. Right, so first we want to avoid ghosts. And so what I mean here when I'm discussing ghosts is that the kinetic term of the theory has the wrong sign, which corresponds to this kappa squared being negative, which again can happen because these masses are evolving. So to avoid ghosts and avoid kind of a total breakdown of my theory, the most conservative thing to do is to require that kappa squared remain positive for the full evolution that we're considering. Which then corresponds, because we want this to be a k-independent statement, to requiring that mt squared be positive definite throughout the whole evolution that we're considering. And then again, this is just the expression there for mt. So if I consider kind of the most limiting case, which is to just set m to 0, here mu is just m over he, where he is the energy scale at the end of inflation. The ghost-free region that gets carved out in this C1, C2 plane is this upper left-hand quadrant here in white. So this is where the theory is ghost-free. So great, sounds good, except there is another problem. So this was a wrong sign in the kinetic term, but we also have that very complicated expression that I showed for omega squared in the dispersion relation. So we can also have a tachyon. So we can also have, in this case, a wrong sign in the mass term coming from this omega squared. And so I've shown again here this expression for omega squared. All of this kind of complicated stuff you don't need to worry about, but this is these are the 2 main terms. And so, of course, having some kind of tachyonic mode is not necessarily a problem. This happens, for example, for minimally coupled scalars. You expect that omega squared oscillates through 0. This can give you some sort of particle enhancement, but is not necessarily a problem. However, in this case, omega squared also has this sound speed modification where CS squared is different from 1. And not only is it different from 1, it can also be negative. And so as a result, having this this potential for a negative sound speed leads to what we call runaway production. And so we can understand that through looking at the dispersion relation for 2 different Ks. So here on the left, I'm showing for a particular mass and a low K mode. This is comparing in blue is the minimal theory, so setting C1 and C2 to 0. The green is C1 and C2 non-zero, but with some very, very small values. such that the sound speed always remains positive. And then the red has larger values of C1 and C2, such that the sound speed goes negative at some point in the evolution. And so here in the blue, we can see that the frequency does go negative, it does oscillate, but towards the end of inflation, we can see that it's well behaved. The green does the same thing, it oscillates a little bit and then settles down. And then the red oscillates a lot, but eventually follows the same behavior. On the right, for a higher K mode, we can see that the green and the blue curves just asymptote to K squared. If you recall, if the sound speed is 1 at high K, the dispersion relation just goes like K squared. So that's all well and good. But this red curve, you can see, continues oscillating through 0 and continues going negative. And so in the context of GPP, you can think about every time this, this dispersion relation oscillates through 0, this corresponds to basically a burst of particle production. And so here we get some oscillations, we get some particle production, and then for the blue and the green at high K, the particle production slows down. For the red, however, going to higher and higher K, the particle production never shuts off. Because we keep having these oscillations, so it keeps growing and growing and growing. And so this is what we call the runaway instability, which is like a gradient instability. And so here we're showing the spectrum of particles produced, so NK as a function of K, comparing the minimal theory, and then the same red curve that I showed on the previous slide. So here for the blue, you can see that it's well behaved, there's a nice peak. And then at high K, it dies back down. And then to determine the full co-moving number density, we want to integrate over this curve. So that's all well behaved.
So you mentioned, is there a typo or is C2 equal 0 equal?
Oh, sorry. Yes, that's a typo. It's negative 0.006.
Okay.
Thanks for pointing that out. Yes.
How should you interpret K here? So I should assume K equals 1 is the mode that exists at the end of inflation, or?
Yeah.
Okay. So I see. So for the standard case, you have some production of particles that's sort of peaking just prior to the end of inflation, and then for the red, there is some subhorizon production of particles. Okay.
Yeah. So then. Right, so what's happening here is the blue is all nice and well behaved, and then the red, of course, is suppressed at lower K, and then as you go to high K, because of this this oscillation in the frequency, you get this runaway production. So this is about 15 orders of magnitude difference in the particle production here, which is of course a big problem if we want to then have this be well behaved and determine the number density. Yeah.
What are the bounds on X1 and X2 set by, say, positivity of energy? Like no energy condition, strong, weak, etc. They also impose constraints.
Yes, that is a good question. We didn't look at that specifically to apply to this, but it is possible there would be some more constraints.
Do you expect this analysis to break down if the particle production is too high since you're linearizing? Okay.
Right. So yeah, so this could also like indicate some breakdown in your EFT where we like can no longer kind of understand the analysis.
Yeah, that also relates to Massimo's question, right? So you don't have background for the gauge fields, correct? Gauge field is just a perturbation on usual FRW background. Hence, effectively, there is no other T mu because there is no background. But once you start producing those particles in huge amounts, that some effective T mu has to satisfy some kind of positivity. And, you know, I guess that's what you are finding on where the runaways are in that consideration. Yeah.
Because I mean, you can ask the standard energy condition, say that for any field configuration, say T mu contracted with
yes.
vector.
Yes.
That may not hold.
That's right. All this, yes.
Yeah, those are good questions that I will have to think about. Okay, so we have we've identified that this runaway is a problem. So we would like to avoid it. And so the way that we can do that is to require that the sound speed also remain positive definite throughout the evolution. So the sound speed again is defined here. So mt squared, we've already required to be positive because to avoid ghosts. And so in order to require that the sound speed stays positive, we also need mx squared to be positive. So again, in this kind of taking m to 0 to get some intuition for where this parameter space is, this carves out this little triangle on the right of the plot. And so you'll recall that the ghost-free region is here and on the top left. And so in this kind of m goes to 0 limit, there's actually no overlap between these two regions. So the only valid point to avoid both this runaway instability and ghosts in your theory is C1 and C2 are both equal to 0. So fortunately, this limit is just for some intuition. We want to turn on this mass and see what that can look like. So fortunately, there is a region where we can avoid both these ghosts and the runaway. So as you turn up the mass, there is a small overlap in these two triangles where we can avoid both of these problems. So here, this is looking, for example, at m over he is 0.1, and there's a very small region of overlap here that is shown in more detail in this inset. So again, this is ghost-free, and then this is runaway-free, and there's some small overlapping region. And then similarly, if we go to m over he is 1, the values of these couplings can get larger. The size of the overlap region gets larger. But the size of this overlap region compared with the size of the couplings and the mass stays constant for any mass.
So let's say I'm trying to figure out what's the mass of that dark photon, right? Is it Niels region or not, right? And then so this is pretty high still, right?
Yes.
So if H is whatever 10 to the 15, we're talking about 10 to the 14 GeV.
Yes.
Photon.
So generally, in terms of gravitational production, you generally think about producing particles that are order Hubble. So like, 10 to the 13 GeV, something like that. But for this mechanism, at least in the minimal case, you can actually get down, depending on kind of what H is for kind of high scale inflation, and a little bit tuning of the reheat temperature, you can get down to 10 to the -7 EV. So there is actually a huge range where these don't necessarily have to be Hubble scale.
I see. So if that number were 10 to the -15 instead of 0.1, you're saying there will be still some overlap.
Exactly, yeah. So this would be the size of this region. The couplings are ordered like mu squared. So the couplings would have to be like 10 to the -30. But there would be an overlapping region.
But this also goes back to the question we sort of asked earlier about the origin of this mass term, because all these things are non-gauge invariant, and you can have, there's some force of shift symmetry, but if you do UV complete it, is there then some relationship between these operators that would then naturally kind of tell you where you want to live?
Yeah, so a great point. So generally, if you were to kind of do out this full calculation to figure out where these operators come from some UV completion, intuitively you would expect that they would be proportional to m squared. So you would expect that as m gets smaller and smaller, if you go to like 10 to the -15 or something like that, you would expect that the couplings are proportional. So we kept it kind of agnostic in this case to not assume that these are coming from anywhere specific, but you would expect there would be some relationship there. And no one's ever like worked that out kind of in analogy to the scalar case, but in principle one could.
I mean, you can do dimension 6 operators. I mean, going by Higgs mechanism would be tough because it would require some crazy small couplings. But through dimensional 6 operators, Cage invariant dimensional 6, which gives you the mass term. You can write that one with some heavy Higgs, and that would be naturally small because it's suppressed to begin with. And then the rest also. Yeah.
But I guess the question isn't just is it small enough to be in this region, but is it the right size to give you something interesting when you have this gravitational particle production? Right. I mean, maybe you can just do an order of magnitude estimate of how big you expect these X's to be given a certain mass, and then is that in the interesting range? Because you're about to tell us that you can get enough of this for dark matter, right? So you need your X's to have the right value.
Yeah. So basically, as long as Xc is like order 1 compared to mu squared, which is m over he. then you end up in this region where, and you can get interesting particle production.
M over HE.
Yeah.
Sorry, what's HE?
Energy scale at the Hubble at the end of inflation. So your scale of inflation.
I mean, I think it's useful to think about some very simple toy UV completions of these operators. So for example, if you had some charged matter charged under the dark photon and you integrate it out at one loop and you pull off two of the gauge bosons and you pull off a graviton, you'd expect these psi's to go like m Planck squared, m squared over lambda to the fourth, where lambda is the new physics I'm integrating out. So it's a 3-scale problem. And yeah, so whether or not you live in this region depends on whether my new physics is closer in log scale to m of my dark photon or m of or in Planck.
Of course, yeah. Yeah, so for different theories, you could have, end up in slightly different regions for sure. Any other questions? Yeah.
Again, on one way to limit to bound this size is if you just take the flat space theory and look at the Stuckelberg fields, the decoupling limit, right, where you look at the longitudinal modes of the gauge fields, and then m squared has to be positive, otherwise you have a ghost in the Stuckelberg, and this other coefficient, the r mu nu, probably psi to r mu nu, probably also has to obey some constraints. But are they the same that you get from trying to avoid runaway production, or are they different, weaker, stronger?
Sorry, the constraints from flat
That
space?
come from just imposing that there are no ghosts around the flat space in the decoupling. So
I see.
Stuckelberg is as positive.
Yeah, but they'll be zero, Massimo, right? So let's say R mu nu, A mu and nu on flat space in the decoupling limit. R mu nu is box of H mu nu roughly, and then
Maybe I should say the decoupling limit of the gauge field, right? Where you just
oh, decoupling of gauge field, sure, but that's the cubic operator. That's a no linear interaction.
No, but you have R mu nu background, so you think of
R mu as flat space.
So yeah, flat space. Let's say non-dynamical gravity.
Okay, so that yes, then you have background, then yes.
Say, are
Yes.
those the same limits actually or different?
I don't know.
So if you think about, say, Stuckelberg propagating in a background inflationary.
Oh, then that's the same.
It's the same.
Oh, that's the same, because for longitudinal part is exactly Stuckelberg.
So
Yeah.
both, I mean, both this unitarity and no runaway production.
Yeah, she has three things, right? So I'm sorry, Leah has three things. One is no ghost, no superluminarity, and no gradient instability, what we call gradient instability.
Okay, so those are exactly the same.
Yeah, those are exactly the same, yes.
Yes, so I think these are the three things that we're thinking about.
Sorry, we use sometimes our lingo, so I was just translating. You said the
Yes.
same thing, so
Thank
I'm
you for
sorry.
the
Yes.
switch. Any other questions? Okay, so we have this region that is avoids these problems. And so you might say, okay, some potential solutions for this. Maybe we can impose a cutoff by hand to say, we're gonna have this analysis is valid up to some cutoff, then we can stop the runaway there. For this to really solve the problem, if you look at where the runaway really starts to kind of take off, you would need lambda to be less than HE during the end of inflation, which is of course problematic if you would like to do perturbation theory during inflation. Again, as was mentioned, you could think about a UV completion. Perhaps this is just an artifact of the EFT. But even in, for example, some abelian Higgs model that you might UV complete this into, we still expect to kind of generate analogous couplings that would lead to this. It's been suggested as well that you could remove these couplings by doing a transformation of the metric, as was asked earlier. For example, a disformal gravity. And so this removes this coupling to R mu nu, which is really the problematic one at tree level, but you still expect this to be generated at higher order. So this doesn't entirely solve the problem. You might also ask about early reheating, if starting reheating earlier kind of truncates this runaway. So in what I've showed previously, we've assumed that reheating is late, so that the universe basically goes from some inflationary quasi-de Sitter era into matter domination, and full reheating happens later. You might ask, what if we go into radiation domination first? What does this do? And so we can look at that as well to see if this runaway still persists. So the runaway is, of course, controlled by basically R over H squared. So this is in this late reheating case that I mentioned, the evolution throughout inflation. And then this is what it looks like in the early reheating case, just for some choice of the reheat temperature and when reheating happens. And what we find is actually that there's not really any difference. So this black curve is the late reheating case that I showed you previously. And then the red is this early reheating. And we can see that the runaway is, a little bit less drastic than it is in the first case, but still not resolved. So this doesn't solve the problem either. Okay, so now I would like to think about this stable region that I showed. And so again, I'm going to define this stable region with exactly these three conditions that we've mentioned. So I'm going to say I want my theory in a region where it's ghost-free, so MT is larger than 0. I want my stable region to be runaway free to avoid this runaway production, so mx squared larger than 0. And then I also want to make sure that the modes are subluminal, such that the sound speed is less than or equal to 1. And so that restricts me to this this wedge of parameter space here, where this is just this color gradient is showing the sound speed, which I'll discuss in a little bit. And so this, again, as I mentioned, this C1 and C2 over mu, if these are kind of like order 1, then this region is stable for a range of mu. So this is the region that we're going to be focused on for the rest of the talk, thinking about kind of dark matter production and phenomenology. Okay. All right, so we want to think about particle production in this stable region. So everything we've talked about so far is for the longitudinal modes. And so we can see that in this stable region, the longitudinal modes are shown here. This is just one example for one particular mode in K, evolution in time. And so we can see that you can approximate the particle production basically to whatever value this asymptotes to. This is what we get for NK. So here the blue is just the minimally coupled case for the longitudinal mode, and then the red is turning on some non-minimal couplings in this well-behaved region. And we can see there's generally an enhancement of the particle production compared to the minimal case. And the same is true for the transverse modes. And we see that we actually get a bigger enhancement here for the transverse modes compared to the longitudinal modes. But these are still relatively subdominant compared to the longitudinal modes. So for the rest of the talk, we'll just consider the longitudinal. The transverse are also there, but everything is really going to be dominated by this. Okay. And so what we can do is think about kind of varying these non-minimal couplings to see what the spectrum of particle production looks like. So here on the left, I've set C2 to 0 and I'm varying C1. So this blue curve is the minimal case for comparison. And then I'm turning up C1 compared to mu squared to 0.1, 0.5, and 0.9. And so we can see that as we turn this up, we get this second peak in the spectrum and an overall enhancement of the particle number. So recall that the full co-moving particle density at the end is the integral over this curve. So this is increased as we turn up C1. We can similarly hold, to get some intuition, hold C1 fixed and vary C2. So if I take this green curve here and put this green curve on this plot, I'm now going to turn up C2, which corresponds to turning up the minimum value of the sound speed. And so compared again, we can see that basically as we get closer and closer to the edge of the stable region, we get a big enhancement in the particle production. And so this makes sense, right? Because as we cross into the unstable region, we expect basically infinite runaway production. And so the closer we get to the edge of this, we can get a big enhancement compared to the minimal theory.
I missed one detail here. So you're assuming reheating to radiation domination, is that it?
So this is back to assuming to matter domination right after a quasi-de Sitter phase, and reheating happens later.
Oh, okay. And the reason these plots are so complicated, I mean, there's a lot of structure in these peaks and so on. Why is that? I mean, A is sort of a smooth function of time, isn't it?
Yes, so the reason that these have basically the second peak is because of the form of the dispersion relation. So in the minimal case, it's just basically k squared is, or omega squared is k squared plus a squared m squared. So you expect this peak right around here. But because there's more structure, you have all of these extra terms and some this additional complication that leads to the second peak at higher k. So basically the peak is shifted because you have this extra structure in like the sound speed.
And if you change the expansion history, so you didn't have this matter dominated phase, or you put radiation or something, you would change qualitatively what this looks like, but you would still have that second peak, or?
So if you went, for example, right into radiation, I believe that this would stay the same. So that was like the previous, the one that I showed for the runaway, the dynamics are very similar. I think probably the second peak would be slightly lower, but it would still be large compared to the minimal theory.
So I might be getting ahead of where you are, you might be getting to this later, but so if to get an interesting signal ultimately, are you going to then have to end up living near this boundary of the instability to get the enhancement you need, or is a moderate enhancement living anywhere sort of in your parameter space going to be okay?
Yeah, so kind of any enhancement is really okay. So the previous papers looking at even GPP in the minimal theory for dark photons found that kind of there's a wide range of parameter space where you can get this to work in the minimal theory. So adding these non-minimal couplings and being able to have this enhancement widens the parameter space a bit more, but you're still able to kind of do this wherever. The knobs you have to turn are basically the scale of inflation and the reheat temperature, and then the mass.
So the blue curve is the Jeremy Martin and Peter Graham paper, right? That's
Yes.
the same spectrum.
Yeah.
So that already could give you the abundance, and you're saying you could change the power spectrum and increase the abundance even. So presumably
Yes.
go to slightly lower masses.
Exactly. Okay, great. Right, so one of these main effects, as I said, is this variation in the sound speed. And so to get a sense of kind of the full parameter space of what this enhancement looks like, it's nice to characterize along contours of constant minimum sound speed. So if I plot directly what the sound speed looks like for a variety of cases, this is here on the left. So the minimal case, the sound speed is just 1. And then for, you can have, for example, this superluminal mode that we've neglected, but just to see an example, it can go larger than 1. But then also I can turn on, again, these non-minimal couplings in the stable region. And then this is what the evolution of the sound speed looks like. So there's this big oscillation right around the end of inflation, and then some further oscillation before it asymptotes nicely to 1 at late times. And so you can think about this kind of in a similar way to people think about sound speed resonances leading to, for example, primordial black holes, things like that. It's similar intuition here. And so this is really where this kind of big enhancement of particle production is coming from. And so we can characterize how drastic this oscillation in the sound speed is by looking at the minimum value of this big first oscillation, which is what is shown here. So each of these curves are contours of constant minimum sound speed in this stable region. So of course, this line here is just 1, and then as we get close to the boundary, it gets closer and closer to the minimum, this oscillation going through 0. And so we can look at particle production and in the context of the relic density in this region. So we can characterize this in the following way. So from our calculation of Na cubed, the co-moving number density, we can translate that into the relic density today with the following, where we want this omega h squared over 0.12 to be order 1 to account for all of the dark matter. And this is dependent again on HE and the reheat temperature. So these are the free parameters that you can move around. And so along these constant contours of sound speed, we calculate this omega h squared over 0.12 with some scaling. And you can see that generally there is this larger enhancement in the number density the closer you get to the boundary, as we would expect from the previous plots. And so again, to your point earlier, what this does is it really kind of opens up the parameter space a bit more to where you can get the correct relic abundance of dark matter. So you can get this, your parameters to tune are kind of M, HE, and T reheat. And so from the minimal case, you're able to have a wider range in these parameters to get the correct relic abundance. Okay, so in the last couple minutes, I'll change gears a little bit and just say a few words about applying these results to the Kalb-Ramond field and Kalb-Ramond-like particles. So the Kalb-Ramond field was first introduced by Kalb and Ramond in the 70s, which is characterized by this antisymmetric two-form tensor B, which has a three-form field strength H. And so you can think about this as basically a two-form analogy to some spin 1 field, right? So in the same way that A mu characterizes point particles, B mu nu characterizes strings, but they have a nice analogy. And so these objects are not just in string theory, they also appear in many areas of physics. And so people often think about the Kalb-Ramond field or this B mu nu as being dual to an axion, which it is in the massless limit. So if this B mu nu is massless, then it is literally just an axion. There's a nice duality relation there. However, if it is massive, so if you put in a mass term like this, it's actually no longer dual to an axion, but it's dual to a massive pseudo-vector field. So you can decompose this field in the following way to basically get back your Proca action. And so from this, at this level, you can see that the GPP, if you were interested in the GPP of these Kalb-Ramond objects, is identical to the Proca case that I just discussed. And you can see this because this is basically a squared interaction. So the fact that this is a pseudo-vector and not a vector doesn't matter. So it's indistinguishable from a dark photon. But what if we turn on non-minimal couplings? So recall that for the Proca field, the two non-minimal couplings that you can write down are to the Ricci scalar and the Ricci tensor that give you these effective masses. For this Kalb-Ramond, you can do a similar analysis and write down a coupling, which I'll call C3 and C4, to, again, the Ricci scalar and to the Riemann tensor, which end up looking like this on FRW. So you'll notice that these look very similar. And so you can actually just redefine the coupling parameters to write these in the same way. And so the effective masses are actually the same on FRW, even though we now have this coupling to the Riemann tensor. And that's true on FRW, but would not necessarily be true on generic spacetimes. So for this Kalb-Ramond field, even when we have the non-minimal couplings, the GPP remains the same. And so everything I just said for Proca with non-minimal couplings also applies here. So I'll just say very briefly to end that there are production mechanisms where these actually are distinct. So if we think about freeze-in, for example, you compare the freeze-in of these Kalb-Ramond-like fields to freeze-in of dark photons in this mass and coupling plane, they actually behave differently because these are kind of fundamentally different objects and interactions. So the scaling of these two things is different. But in the context of GPP, they're indistinguishable. Okay, so I think I'm almost out of time, so I'll just end here with my summary and conclusions. So we've discussed adding these non-minimal couplings to gravity when considering the GPP of dark photons and shown that they can lead to these instabilities, ghost instabilities and this runaway instability. There is a region of parameter space which is both ghost-free, runaway-free, and subluminal. where we can get the correct relative abundance of dark matter. And then adding these non-minimal couplings basically opens up the parameter space a little bit more, where you're able to get this correct dark matter abundance. And then I've also just briefly mentioned that these results can be applied also to Cal-Bramone fields and Cal-Bramone-like particles. So with that, thanks so much for your attention, and I'm happy to take more questions.
Questions?
I guess one question is, did you consider couplings to the inflaton rather than just to gravity?
So we have not done that in this case. So this was kind of just the simplest thing that you can think about, where you have inflation and then just some like background kind of spectator field on top of it. But you certainly could couple this directly to the inflaton as well. And I think you would have similar dynamics, perhaps some similar instability, but we haven't looked at that. That's a good idea.
I guess if you have 5 of dual type stuff, then you can have extra tachyonic instabilities. Other questions?
So what,
This is a potentially really stupid question, so forgive me, but in the Cal-Bramone case, would there be 2 ways you can couple to the Riemann tensor quadratically? Right, like the index structure? Right, like you could match like with one of them mu and rho and then mu and sigma, and that would be non-zero, right?
Yes, I think that's true, but actually in this case, it doesn't make a difference because on FRW, because it's conformally flat, like the
Okay,
symmetries of the
sorry.
spacetime, this just reduces anyways to the Riemann tensor and the Ricci tensor. But you could, yeah, in principle, on a more general spacetime, write something else down.
Sorry, just to this question, but those 2 options are the same by Bianchi.
Maybe yeah.
one
I'm
of
sure
them
it'd be
being here, the one that-
Okay, yeah, like this, so, okay.
The
Yeah,
community
I see,
indices.
yeah.
So why spin 1? I mean, what's different here you have between spin 1 and spin 0 or 1/2? What?
Yeah, so we were interested in this in terms of thinking about kind of dark photons as a dark matter candidate. The spin 0 and spin 1/2 cases have been worked out in a lot of detail, like over many years. And so we were interested in thinking about this dark photon in terms of just, an interesting dark matter candidate. You could do similar analysis, of course, for the other 2. They don't exhibit these same kinds of instabilities. So this ended up just kind of being a little bit more interesting.
Maybe also you can have it with low mass and it's technically natural.
Yes.
Low mass dark matters.
I mean, but also I like that. I mean, we had this models of minimal supergravity inflation where you naturally get a mass. I don't have anything against that.
Other questions?
Thank you.
Yep.
So I know a long time ago, I don't know what the current status is with this, but like when people consider production of topological defects, like from reheating, right? Like if your scale of symmetry rating is slightly above, say, the inflationary Hubble, then like people had cooked up these models that had these like crazy reheating scenarios where like the temperature was not at all homogeneous to begin with, like very far from the instantaneous reheating approximation that people often take. And I'm assuming you can like do crazy stuff with your model where you make reheating totally crazy and completely change its production, so how much you produce and so on. Is that?
Yeah, so again, we just considered kind of like a very standard reheating model. You can always do crazy things and see how that would change it. Here, because the majority of the particle production is happening right at the end of inflation and not actually during reheating, I don't know really how much it would change, but it is possible, maybe you have this huge enhancement and then you have something happen during reheating that actually can bring it back down. So it's always possible, but yeah, we just looked at kind of the standard case.
Maybe I'll ask some sub-leading question. So these are smaller effects, your effects are bigger, but let's say the production of perturbations which happened before or way before end of inflation. Well, they will have longer time to redshift, unlike the ones that are your main effect, right? So that means that they'll be entering later into your horizon. Let's say, I don't know, during radiation domination or maybe even matter domination, I just don't know. There'll be smaller effects compared to your main effect, but still, there might be something interesting about that.
Mhm.
I don't know if you looked at that.
Yeah, so we didn't end up, we didn't look at that, but that's interesting to think about if potentially there's some effects occurring later as well. That would either add to this or maybe kind of alleviate things.
Could you comment a bit on the UV completion for the Calvert-Mont case? Like, should I, for the spin-on, of course, I mean, you can fix it, but
Yeah.
is there a similar understanding for the Calvert-Mont?
Yeah, so in this case for the Calvert-Mont, again, we just considered it as an EFT. Depending on who you ask a bit, I think there's not necessarily a good UV completion that's not like string theory. So I think kind of beyond that, mostly people just think about it in terms of the EFT, but yeah, it's a good question.
Okay, looks like no other questions, so Cynthia again. So in that case,
Thank you.
in that case, it's just fixing it.
So in the
Well, I mean,
main,
you have a solid
no,
million
frame
vectors.
or then
The
just have
visual-
the.
I mean, sometimes there are different couplings you could add that may just not
Yeah,
be like.
no,
that.
I'm very good with that.
The degrees of freedom is still the same.
Now you're
Yeah.
I say make
Right,
it
I
just
guess
a
I-
local interaction.
Yeah, so
That
basically like the main scenario we considered was that just like
Not really.
reheating happens
like,
like after the state
Anytime
particle
you see an
production
insertion
has
of Ricci.
been done.
Right, that is.
Um,
usually
nothing
not-
more
Well,
happens.
there's different
Higher
questions you
Particle
wanna
production
ask.
finds during reheating.
One of them
The
is to
early reheating case is to say,
handle all non-runaway
reheating
operators.
happens,
One is
like,
to handle
first.
the gauge.
Right.
and
Yeah,
that,
those
you
are
know,
kind of like, I
changes
think,
things a
for like
little
a
bit,
normal
but
EFT,
qualitatively it
You're
remains the
supposed
same.
to accept the non-normalizable operators.
But yeah, one could certainly consider like
But being able
different
to
reheating
receive
scenarios and see what would happen
intact
there.
way, which.
Right.
Does this impact at all Curly's? It doesn't. Curly's objections to.
Yeah, we chatted a little bit. So Curly's objection is if you have a large enough kinetic mixing, right? Because that automatically implies a large gauge coupling and therefore a small Higgs bed. And then if you have these early universe types of production, then you have this vortex production, which would also apply here.
But just
but-
because
but-
they have this bigger parameter space.
Well, and Leah in principle could take the gauge coupling to 0 and the Higgs vev to infinity above the inflationary scale, or